Light, the source of everything our eyes can see. This wave of energy travels from lamps to our eyes, from distant stars to our planet, and illuminates the screens around us. And it has a speed, but that speed is more than just a number. It's a boundary of the universe, a limit that cannot be crossed. When defined in physical terms, the speed of light in a vacuum is exactly 186,000 miles per second. That's fast enough to circle the Earth nearly 7 times in just 1 second. It takes only 1.3 seconds to reach the Moon, about 3 minutes to get to Mars, and just 8 minutes to arrive at the Sun. For light, distance is no obstacle. Time itself can stretch. But when you begin to approach that speed, physics starts to change, reality begins to warp, and everything familiar starts to fall apart. So what makes the speed of light so special? And why does physics treat this number as the universe's ultimate unbreakable limit? The answer lies in Einstein's theory of special relativity, introduced in 1905. According to this theory, the speed of light is constant for all observers in the universe. Whether you're standing still or moving at hundreds of thousands of miles per second, you will always measure light traveling at the same speed. And this constancy is one of the foundational principles on which the rest of physics is built. From the way time flows to how mass behaves, everything depends on this fixed value. Now imagine this. You get into a vehicle and accelerate to nearly the speed of light, around 186,000 miles per second. It may sound like something out of a science fiction movie, but this is where things become even more fascinating. Because at that speed, time begins to slow down. Mass increases, the world in front of you starts to bend, and eventually even light itself seems unable to keep up with you. In theory, reaching the speed of light isn't impossible, but in practice it would mean directly challenging the laws of nature. That's because any object with mass, like you or anything made of matter, experiences an exponential increase in mass as it approaches that speed. And the energy required to accelerate it rises just as dramatically. Eventually, that energy reaches infinity. In other words, to reach the speed of light, you'd need to harness all the energy in the universe, and even that might not be enough. That's why the speed of light is more than just a speed. It's a boundary, an invisible line drawn between matter and light, between past and future, between time and space. On our side, the laws of physics apply. But the other side? That remains a mystery. Now let's stretch your imagination a bit further. You're inside a spaceship. Your mission, to get as close as possible to the speed of light. At first, you accelerate slowly. A journey that begins at just a few thousand miles per hour quickly rises to hundreds of thousands of miles per second. Everything seems normal at first, but there's a threshold. And once you cross it, your surroundings begin to change. The first thing you notice is that the scenery around you starts to distort in strange ways. The stars in front of you appear dimmer, yet somehow sharper. Their colors begin to shift. A bluish glow, an ultraviolet shimmer starts to flood your view. But when you turn around, you see an entirely different picture. Light seems to fall behind, as if it can no longer catch up. This experience is called the Doppler effect. Just like the pitch of an ambulance siren drops as it moves away from you, light from receding objects shifts toward red. Everything you approach shifts toward blue. But as you near the speed of light, this effect becomes so intense that the colors you once knew begin to vanish. Your field of vision narrows. The universe curves ahead like a tunnel. At this point, your perception begins to deceive you. When you turn your head to the right or left, what you see changes instantly. That's because photons coming from different directions are delayed on their way to your eyes. Nothing you're seeing in that moment is truly there in that moment. Everything comes from the past. Everything is a delayed image. So what would we feel during a journey like this? Would we feel ourselves moving through space, or would it feel like the world around us is disappearing? Some physicists describe this condition as perceptual intoxication. The flow of time, the appearance of the outside world, and your sense of direction all begin to fall out of sync. Even if you know exactly which way you're looking, you can't be sure that what you're seeing is actually in that direction. Because at this speed, space itself has become distorted. And your eyes, your brain, your senses, they're all still operating by the old rules. But amid all these distortions, one thing remains constant. You're still accelerating. And with every passing second, you're one step closer to the speed of light. But just before that final step, something more dangerous lies ahead. Because light isn't the only thing out there. And space isn't as empty as you might think. Space, it's often described as a vacuum, silent, still, and completely empty. But that description only holds true until you approach the speed of light. Space is far from empty. On the contrary, it's filled with countless invisible particles. In just 1 cubic meter of space, there are an estimated 10 million atoms. That number might sound small, but near light speed, these atoms become bullets. Nuclei of hydrogen, helium, and even trace amounts of oxygen race toward you at hundreds of millions of miles per hour. At that velocity, they don't just damage the ship's surface, they can pierce through its entire structure. And the collisions don't result in ordinary mechanical damage. Each impact can unleash the force of a microscopic nuclear explosion. And it's not just atoms you have to worry about. There's also something far more deceptive: dust particles. If a spaceship traveling near the speed of light were to collide with a single dust grain just a few microns wide, it could trigger a disaster. The impact could release as much energy as a thermonuclear bomb. That means millions of degrees in temperature, intense radiation, and a shattered hull. Worse yet, detecting these particles in advance is nearly impossible. That's why a phrase often repeated in the scientific community goes, "Before humanity reaches the speed of light, space will stop it first." But let's assume we overcome all these challenges. The ship is intact, radiation is under control, and no collisions have occurred. So what happens now? As you draw nearer to light speed, a force as dangerous as particles and atoms begins to emerge: time itself. In our daily lives, time feels constant. Minutes, seconds, hours, they all pass at the same pace. But that's merely an illusion that holds true only at low speeds. According to Einstein's theory of relativity, time slows down as you accelerate. And this doesn't just apply to clocks, it applies to you. If you're inside a spaceship nearing the speed of light, 1 hour for you could mean weeks, months, or even years passing on Earth. This isn't just a theoretical idea. Astronauts aboard the International Space Station already experience this effect, albeit only by a few microseconds. But as you get closer to the speed of light, this difference becomes impossible to ignore. And it's not just time that changes. Your field of view, your perception of space, even your sense of direction begins to distort. Objects ahead of you appear warped, as if viewed through a powerful lens. Everything you see with your eyes becomes a reflection of the past. That's why an observer traveling at near-light speeds can no longer perceive distant objects in their true form. Earth would no longer appear as a sphere, it would flatten into a disk. The entire universe would seem to tunnel forward, stretching ahead, narrowing from the sides. And behind you, nothing remains, because even light can no longer keep up. Inside the spaceship, everything might seem normal, but outside, the universe is aging rapidly. Time bends, space warps, and the universe reshapes itself before your eyes. Your journey toward the speed of light has reached a point of no return. But at that very moment, physics throws up an unbreakable wall, and that wall is called relativity. Einstein's special theory of relativity doesn't just declare that the speed of light is constant, it also states that this speed can never be surpassed by anything with mass. But why? Because as you accelerate, not just time, but mass begins to change. In reality, your physical structure doesn't actually alter, but the energy you expend to accelerate starts behaving like mass. The faster you go, the more energy you need, and that energy in turn makes you heavier. This feedback loop gets worse the closer you get to the speed of light. In a way, by accelerating yourself, you're also increasing your own weight. It's like climbing a mountain while someone adds more weight to your backpack with every step. Eventually, you reach a point where, no matter how strong you are, taking one more step becomes impossible. At the speed of light, this reaches an extreme, because theoretically, to reach that speed, you would need infinite energy. Yes, you heard that right, infinite. So forget about going faster than light. Just reaching it would require consuming all the energy in the universe. And clearly, that's not feasible in practice. But is this an absolute rule? Has the universe categorically forbidden us from reaching the speed of light? Based on what we currently know, yes. And this limit doesn't just apply to us, it applies to everything. No particle in the universe, not protons, electrons, neutrons, or even stars, can exceed the speed of light. They all remain below that cosmic limit. Still, humanity hasn't given up on trying to break it. The speed of light may be a physical boundary, but the human mind has never been content with boundaries. For a species that has dreamed of the stars for thousands of years, staying confined to a single galaxy is not an acceptable fate. That's why some physicists, instead of trying to directly exceed light speed, have begun exploring ways to bend the rules of the universe itself. One of the most intriguing ideas came in the mid-1990s, proposed by Mexican theoretical physicist Miguel Alcubierre, the warp drive. The concept was originally a fictional technology in the Star Trek series, but Alcubierre took it seriously and managed to root it in the mathematics of Einstein's equations. The warp drive works by compressing space-time in front of a spacecraft and expanding it behind, creating a sort of cosmic bubble. The spacecraft itself doesn't move, but because the space around it does, it appears to travel faster than light, and it does all this without actually reaching light speed. Technically, the ship isn't moving at all, yet its position is changing. In theory, it's possible, but in practice, it runs into a massive obstacle: energy. To make this system work, a substance with negative energy density is required, and such a substance has not yet been discovered anywhere in the universe. In other words, the warp drive remains, for now, nothing more than an equation confined to the whiteboard. A similar idea was proposed by Russian physicist Sergei Krasnikov. According to him, a spacecraft must first travel along a route at ordinary speed. Then, after that journey, a kind of cosmic tunnel should be created along the same path. And on the next trip, this tunnel could allow the journey to be completed in a time that appears faster than light. This concept, known as Krasnikov tubes, works, at least theoretically, based on the principle of bending space and time. But here too, the same issue arises. The amount of energy required defies imagination. To power a ship using this method, one would need to generate negative energy equivalent to hundreds of Jupiter masses. And right now, no one knows how to produce such energy. All right, surpassing the speed of light with a physical object seems nearly impossible. But what about information? A thought, a message, or a signal? Could these cross the universe's speed limit? For a long time, physics had a clear answer to this question: a resounding no. But in the mid-20th century, quantum physics came into play and showed that nothing is ever quite as simple as it seems. At the heart of this debate today lies a quantum phenomenon: entanglement. Quantum entanglement occurs when two particles become so deeply connected that no matter where they are in the universe, they respond to each other simultaneously. When one is measured, the other's state is instantly determined. That word "instantly" is crucial here, because no matter how great the distance between them, the exchange of information appears to be independent of time. In 2022, the Nobel Prize in Physics was awarded to scientists whose experiments proved this phenomenon. Their findings showed that no classical signal travels between entangled particles. Entanglement truly occurs in real time. So in that case, could interstellar communication become a reality? Could we, for example, establish instant communication with Proxima b, the closest Earth-like exoplanet? In theory, yes. For example, if a quantum envelope is opened on Earth, its entangled counterpart on Proxima b could instantly undergo a change, as if the information travels to the other planet, completely ignoring the speed of light. But here, a critical problem arises: context. Opening quantum envelopes only produces a result, but that result carries no meaning unless you already know what information was encoded and what you're expecting. In other words, if the message you're trying to send isn't already known by the recipient, it becomes meaningless. Quantum entanglement only carries random information. It cannot convey intentional meaning, the sender's intent, a word, or a sentence. And when we examine this kind of instant communication in terms of cause and effect, things get even more complicated. This is where the Minkowski diagram comes in. This diagram represents time on the vertical axis and space on the horizontal. Anything moving at the speed of light travels along a 45-degree angle on this graph, so a light signal sent to Proxima b would move along that diagonal. Now let's imagine you're trying to send a message faster than light. On the diagram, that would appear as a line closer to horizontal. And right there, a time paradox emerges, because this message could reach its recipient before you even send it. In other words, a thought written in the future could receive its answer in the past. What does this mean? One perspective says it implies the universe allows contradictory events to occur. Another suggests the universe automatically renders such communication meaningless to prevent those contradictions. Breaking the speed of light remains an unpassable boundary for us. But that doesn't mean no other entity in the universe could have crossed it. And what if someone has already done so? What if they're watching us right now? The Milky Way galaxy alone contains hundreds of billions of stars. Orbiting those stars could be trillions of planets, some dead, some boiling with volcanoes, others covered in ice. But some might be very similar to our Earth, and if just one of them hosted intelligence that emerged millions of years before us, that intelligence might have already discovered how to surpass the speed of light. But the gap between such a civilization and us would be as vast as the gap between a human and a bacterium. Because surpassing the speed of light isn't just a technological feat, it means having command over the structure of the universe. Such a civilization could travel not only through space, but through time. It could control mass, redefine energy, manipulate physical layers we can't even perceive. Then why hasn't such a being contacted us? Maybe it has, but we simply can't perceive the message. Because even if you left a letter for an ant, the ant wouldn't be able to read it. It might not even comprehend the existence of the letter. And perhaps we are currently in that same position. There's another possibility. Perhaps they're only observing us, watching but not interfering. Because disrupting the evolution of a civilization could halt its natural development. Just like a camera placed in the wild, you observe, but you don't interfere. But the most unsettling possibility might be this: they don't consider us important. Because if there are millions of advanced civilizations in the universe, how interesting could a species really be if it hasn't even reached its own star and is still struggling with the basic laws of physics? Still, we stand at the threshold of an unknown so vast we haven't even cracked open the door. And surpassing the speed of light may be the first step through that door. But once that step is taken, not only where we are, but who we are could change forever.